Okay, so welcome back. And now that we've covered infinite sequences, now let's talk about infinite series. Okay, so let's start with the infinite sequence. So like before, an infinite sequence is a sequence of terms, right? So again, we represent this sequence in this notation, and it's just an infinite sequence of numbers that keeps going on. Okay, so we've dealt with those at length. Okay, now what is an infinite series? An infinite series is just taking a sequence and now we're just adding up those sequence of terms. So now we're dealing with an infinite sum, okay, of a sequence of numbers, if you will. So now the thing is this is an infinite sum, so how do we deal with that? We can't just add them up the way we do a finite sum. So what are we going to have to do? Well, we're going to focus on what we call partial sums. Okay, so what is a partial sum? Well, it's just a finite sum of terms of an infinite series. So a finite sum, look, for example, s of k would represent a finite sum up to the kth term. Okay, so this would be the sum from n equals 1 to k, so it would represent this finite sum. We call it a partial sum. Okay, so what are we going to do with partial sums? How are we going to use partial sums to help us decide what's going on with the infinite series? Well, let me give you an example. Let's say that we have this lake and there's oil that's being dumped that's seeping into this lake at a certain rate. And let's say the first week, 1,000 gallons falls into the lake, or seeps into the lake. Okay? And then the following week, let's say 500 gallons seeps into the lake. And then the next week, week 3, 250 gallons seeps into the lake. And then week 4 goes down to 125. And you see where I'm going with this, right? So basically half as much oil is seeping into the lake as the week before. So what do we have? We have something like this. So in this example, let's say we're dealing with thousands of gallons per week. Okay? So let's say that week 1, you have 1, right? Then you have week 2, you have 1 plus a half. So this is the amount of oil that's seeping into the lake total, right? After each week. And then you have, week 3. Plus 1/4. Right? And then you keep going. Let's say you have week 4. You end up with a total amount of oil that's seeping into the lake. Oh, sorry. It should be... Okay. And then week 5, you've got 1 plus a half plus a 4th plus an 1/8. Okay, and so this, again, this progression from week 1 to week 5 represents the total amount of oil that's seeping into the lake from the beginning. Okay, so after 5 weeks, this is how much total oil has seeped into the lake, and it keeps going on like this. So half as much is going into the lake every week. Okay? So now looking at this pattern, we can see that after K weeks, the amount of oil that's in the lake can be represented by this. So after the Kth week is going to be the sum of what? Well, let's do it this way. So let's say week K down. Yeah, let's do it this way, sorry. So week K, so the partial sum, let's go to week K, is going to look like this. So it's going to be 1 plus 1/2 plus 1/4 plus 1/8, and it keeps going, dot, 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 and it's going to be 1 over 2 to the K minus 1 power. Okay? Why? Because when K is 1, you get 2 to the 0, which gives you 1 over 1, which is 1. When K is 2, the second week, you get 1/2. For the third week, you get 1 over 2 to the second, and so on. So the nth term, if you will, of the sequence, if you want to think about the sequence, is going to be here. Okay? So, nope, this should be, is that what I want to do? Yeah, yep. So now, what does this equal? Well, this partial sum, again, it can be written as a sum, right? So it's a partial sum. So we can write this as a sum from what? N equals 1 to K of what? Well, this is going to be equal to 1 over 2 to the what? N minus 1. Okay? So that represents the partial sum for this example. Now, what we're interested in is what happens as K goes to infinity. Okay? So we can write that this way, right? So we can write that, let me go back to here. So we can write that as n goes from 1 to infinity, like that, right? Okay, and of course this is just going to represent the infinite sum that just keeps going on and on and on. Okay, but how do we evaluate these series? That's the question. So at the same time that K is going to infinity, the amount of oil in this example can be calculated by evaluating the limit. what is the limit? Well, the limit of the partial sum, right? So we could take the limit as k goes to infinity of s of k. So, therefore, the behavior of the infinite series can be determined by looking at the behavior of the sequence of partial sums. Right? Because for each k, we're going to have a different partial sum, right? For each k, we're going to have a different partial sum. And what we can do is we can take those partial sums for each value of k and create a sequence of partial sums. And then what we can do is we can apply all of the things that we've learned in the previous section about infinite sequences to this situation. Because then what we can say is if these partial sums are converging to a number, then we know the infinite series is converging to that number. If the infinite sequence of partial sums is diverging or is divergent, then we know that the infinite series is also divergent. And so a lot of the things, everything that we learned about infinite sequences can now be applied to evaluating infinite series by looking at the sequence of partial sums. Now, again, if the sequence of partial sums diverges, then we say the infinite series diverges. Okay? If the sequence of partial sums converges, then we say the infinite series converges, and we can give the sum by using the limit notation. Okay? And we can find what that sum is. Okay? Now, in our example, let's look at what we have. So, back to the oil, right? So if we look at S sub k for each k, right? So we know that S sub 1 equals 1, S sub 2 equals 1 plus a half, which equals what? 3 halves, so 1.5, or 3 halves. Okay? And then partial sum number 3, so we go 1 plus a half plus a fourth. Okay? And so what is this going to equal? This is going to equal 2/4, right? Which equals, this case is going to be 2/4 plus a fourth is 3/4. 3/4 plus 4/4 is 7/4. Okay? And then when you do S sub 4, it goes to 1/8. Okay? And if we put that out, we get 15/8. And then if we go out to 5th, we get what? 31/16. Okay? And if we go out one more, we get what? Okay? And we can keep doing this, right? And I go further than the book, because then you start to see a pattern. Okay, and so it seems like looking at the sequence of partial sums, right? So what is our sequence of partial sums? Let's write it out. So we got 1, 3/2, 7/4, oops, 15/8, 31/16, and there we go. And then it keeps going on and on, right? So it goes 1, 3/2, 7/4, 15/8, 31/16, 63/32, and 127/64. Okay, so now, with exception to 1, it seems like all of these is very close to. Okay, in fact, it seems like, with the exception of the first term, right, which is 1, all the other terms seem to be getting closer and closer to 2. So it seems like the limit of the partial sums is 2. Okay? And if you do this in your calculator, you can get a table and you can see that this is getting closer and closer to 2 when you look at the table values. Okay, so now, so again, if you stick this in your calculator, you can calculate even more, and you can even more convinced that this thing seems to be heading towards 2. Okay, now, later on we're going to talk about a more analytic argument that will prove that the limit of the partial sums of this example is 2. Okay, so what we're going to do is we're going to rely now on just the numeric evidence and the graphical evidence, so you can plot this and you can see that this also seems to be approaching 2. You can use your calculator and create a table of values in where you're going to see that this thing is going to be getting closer and closer to 2. Okay. Now, since the sequence of partial sums converges to 2, then what we say is the infinite series converges to 2. And so what we then write, okay, again, we're going to prove this later, analytically, but right now let's just say, hey, this thing converges to 2. So what do we say? We say that the sum, the infinite series, right? This infinite series from n equals 1 to infinity of, oh, how do they write it? Yes. Equals 2. Since the infinite sequence of partial sums converges to 2, then we would write that the infinite series, which is expressed by this, is equal to 2. And that's the answer. So basically, returning to the question of the oil in the lake, what does that mean? It means that since the series converges to 2, that we can say that the amount of oil in the lake is going to be arbitrarily close to 2,000 gallons. Okay, as the amount of time, in this case, the number of weeks becomes sufficiently large. Okay, so this is an example of a geometric series. Okay, we've talked about geometric sequences, right? So we will discuss geometric series in more detail later. And let's see, I think that's all I want to do. So next is we're going to introduce the definition. I'm going to introduce the definition of an infinite series, and then we're going to go from there. Take care.